right, well, let's do this. Welcome back, folks. Happy Thursday. Um, as you'll remember, we've been working with parallelograms and how to use parallelograms, as well as how to prove that something is a parallelogram, or if it's given as a parallelogram, how to prove that certain attributes are true. I had shown you that family tree effectively that demonstrates that there's a family of parallelograms, a number of shapes that qualify as parallelograms, rectangles, rhombuses, and squares. And today, that's what we're going to learn about. To get into that, I'd like to share a little story about a rectangle that's kind of fun. So there was this mother, and she expressed her love through baking. And she had twins. And of course, if you have twins, you have to give them exactly the same of everything. And they had had a long week at school, and as the week was winding up, she decided to bake them some brownies. So she baked them a tin of brownies, and they were cooling on the counter, and she was all excited to give the kids the brownies. And of course, she would just slice it in half and give each half so that they get the same amount. But while she was out of the room, the husband came by. And darn that husband, he wanted some brownie too. So he decided, I'll just cut out a little piece. There's plenty there. And so he cut out a little piece of brownie that he could enjoy. And now mom is stuck with the decision. How can she possibly cut this thing with just one cut? Because she's kind of lazy now. So that each person gets exactly half the brownie. Now, please don't go trying to tell me that you can slice it this way, because we all know that the top of the brownie is so much better than the bottom of the brownie. Those are not equivalent. But how could I slice this rectangle, given that it's got a rectangular hole cut out of it, so that with one slice, I get two even parts? Any ideas? I think to dig into this a little bit, I want to kind of propose a few things. Let's say I take just a regular triangle, no hole cut out of it. How could I slice it in half? Not a trick question. What could I do to slice that exactly in half?
Go from corner to corner diagonally.
You guys agree that that would slice it in half, and you'd end up with two triangles, each the same size. And I could do that same thing from the other diagonals, couldn't I? Is that it? Are those the only ways I can cut these things in half? What else?
You could draw a line through the middle.
From the top? So like a vertical line cutting it through, right through that same point. Good. Anything else? Squiggly line. Interesting idea. The challenge with a squiggly line is how would you ensure that it hits exactly half?
You can cut it horizontally.
Good. We could cut it horizontally. So is that it? Just 1, 2, 3, 4 ways? Notice they all go through some central point here, right? They all go through the center of the brownie. What if I just randomly slice through that center spot? Would that cut it evenly in half? It wouldn't it? There's a proof in there that we could do with that, talking about right angle here and right angle here and right angle here and right angle here. And this is alternate interior to that, and this is alternate interior to that. This is the same side as this. And there is a proof to this that we could do to demonstrate that those cut in half. But I'm going to cut to the chase here. Turns out that no matter how you slice through that center point, if you go through that center, every single line you do will cut it exactly in half. It's a rare attribute associated with rectangles. Does that help us with our brownie problem? Because I know there's a bunch of ways I can cut the big part in half. But how do I also make sure that that part is cut evenly in half? Brownie's going to get stale. Well, do we agree that we're going to have to go through the middle point here because that's going to get the middle of the whole thing? How do we get the middle of the whole? Could we do the same thing? Figure out the two diagonals, and that would be the middle of the whole? And we know that any line that goes through the center would slice this in half, right? So what if I just keep rotating it until it's the line that goes through that center that also goes through the hole? Wouldn't that both cut the whole brownie in half and also cut the hole in half? So each kid gets the brownie less half the hole. Anyway, kind of a fun little start, a cool feature of rectangles. But what we're going to talk about today is not brownies, unfortunately. We want to look at a rectangle and figure out what's true about it, what's new about it. So first, what defines a rectangle? It's part of the parallelogram family. In other words, it satisfies all the parallelogram natures. But it's got something else. What's the unique attribute that a rectangle has that a parallelogram does not?
The angles are all form right angles.
Exactly right. All four of them are right angles. And when you customize your parallelogram by adding all four angles right, it forces it to be a shape called a rectangle. How is that valuable to us? Well, you'll remember the proofs that we did in parallelograms often let us look at triangles being congruent. So could we prove these two triangles to be congruent? Sure. I mean, we were able to do that in parallelograms, right? That's how we would get the CP-CTC to prove our attributes. But what's unique in this case in a rectangle is that because we've got these angles being right, consecutive angles are not just supplementary, they're actually congruent now. So I can also draw this triangle. And if I take this triangle and this triangle, I should be able to prove them congruent. Any ideas how we can get started? Well, because it's a rectangle, these are right angles, which means each triangle has a right angle. We've got an angle that's congruent. They also share this bottom side by reflexive. But that's only two pieces of information. Is there a third piece I could also get? Well, the fact that these two are right angles means they're consecutive angles that are supplementary, right? It's parallelogram. So these lines are parallel, and these two are supplementary, meaning these lines are parallel, which means it is a parallelogram, which means that we know that opposite sides are congruent. So now I can end up with the red triangle and the orange triangle are congruent by what theorem?
SAS.
Very good. SAS, SAS. And of course, if they're congruent, I can say that by CP-CTC, corresponding parts of congruent triangles are congruent, I can say that any other corresponding parts are congruent, such as the diagonals. Going from one corner to the other is the same length now that it's a rectangle. That wasn't true in a parallelogram, was it? If I had a parallelogram that looked like this, what I'd find is that this is a shorter diagonal and this is a longer diagonal. It does get bisected. But here we're saying that not only does this get bisected, because it's part of a parallelogram, but this other length is the same. And so when it gets bisected, you end up with these four little arms sticking out that are all the same length. All right, so that leads us to the notes for today. What we're talking about with rectangles is that because they're part of the parallelogram family, they contain all the attributes of a parallelogram. Opposite sides are congruent, opposite sides are parallel, opposite angles are congruent, consecutive angles are supplementary, and diagonals bisect each other. But because it's a rectangle, we've got a new definition component, which is that it's got all four right angles. All four of the interior angles are right angles or 90 degrees. And the one we just came up with. The diagonals, not only do they bisect each other like they did for the parallelogram, but the diagonals are congruent. So part of today's homework will be for you to do problems like these, 1, 2, 3, 4, and 5. I'd like to do a couple of these with you now. Let's do problem 2 together. We're given a picture, we're given AE, we're given DC, and we're asked to find AC. Can somebody please tell me how you might find AC and justify your value? Well, remember that we ask ourselves, is it an angle, a side, or a diagonal I'm looking at?
It's a diagonal.
Good, it's a diagonal. And we now have two things associated with diagonals. They bisect each other and they're congruent. Which one of those is helpful to us now for AC?
The second.
You think it's helpful that the diagonals are congruent so that this orange one would be the same as DB. But we don't know anything about DB. I think it's more helpful to know that the diagonals bisect each other. So if DB is slicing this orange one exactly in half, so AE is 15, how big is EC?
15.
Also 15. And when we do AC, then we can leverage back to what we learned first semester, the segment addition postulate that says that this whole length is this part plus this part. So 15 plus 15, AC should be 30. Second question asks for BD. Okay, so ask ourselves again, is this a side, an angle, or a diagonal? It's a diagonal. This time it's a whole diagonal. So how long is that?
30 degrees.
It's 30, I shouldn't have put degrees, should have I? That's a mistake up there. It's 30 units, whatever that is. Good, and BD is the same length, right? So it's also equal to 30 because it's the same as that one above it. Both diagonals have the same measure. And What about BE? Still dealing with the diagonal.
Wouldn't it just be 15?
Yeah, it's just half of that diagonal because now we're saying diagonals bisect each other. So we'd say I take 30 divided by 2, that would equal 15. What about AB?
27.
Good. How'd you know that, Joe?
Because it's the opposite. DC and AB are the exact same length, and so if DC is 27, AB is also 27.
Good. Exactly. We know that opposite sides in any parallelogram, whether it's a rectangle or just a regular parallelogram, are going to be congruent. So if that's 27, so is that. The last one, this one's a little harder. What about BC? There's one more element to being a rectangle that we haven't leveraged yet today. It's part of the definition. What more do we know about this triangle? This is a right angle, isn't it? Good. And if it's a right angle, then we know we can apply the Pythagorean theorem. A squared plus B squared equals C squared. Does it matter which one's A, B, and C? The green one has to be C, right? That's our hypotenuse. That's the only real restriction. So I'm going to say 27 squared plus equals plus BC squared equals 30 squared. So 729 plus BC squared equals 900. So BC squared equals 171, which means BC is equal to the square root of 171. And that's a precise answer. We'll deal later with how to simplify that, but it's probably a good idea to give a decimal approximation. So after that, I'm going to put a little squiggly equal sign to say that it's being rounded. 13.08. I'm rounding that to the nearest 100th. Any questions on this first problem we did? Okay, let's take a look at number 3 as well, because that deals more with the angles rather than the sides. First, we're doing MJK. MJK. How big is that angle?
90 degrees.
Sure is. It's a full interior angle, which in a rectangle is 90 degrees. This time it does get a degree symbol. Okay, what about MJL?
Would it be 63 degrees?
Good, because we know that that plus 27 together make up the whole 90-degree angle, don't they? So that would be 63. What about JLK? Add that in there. JLK. So now we want to find this one.
Wouldn't it also be 63?
Good. Why?
Because it's congruent with MJL,
Good.
and they're the same.
Because they're AIA, right? Alternate interior angles. Okay, what about KML? That one takes a little creativity. So we know that these diagonals are both congruent and bisected, aren't they? So this length is the same as this length, is the same as this length, is the same as this length. Which means that each of these little triangles is isosceles. So if I know that this is 27, I can find my alternate interior down here and say that's also 27. And I can say that if this triangle is isosceles, then we can apply the isosceles triangle theorem to say that base angles are the same. So if that's 27, so is that. So KML is 27 degrees. What about MNL?
Would it be 126?
It would, good, because we see that it makes a triangle, right? So we'd say 27 plus 27 plus measure of angle MNL equals 180. So 54 plus measure of angle MNL equals 180. So the measure of MNL equals 126. How do you feel about rectangles? Give me an answer in the chat, please. 5, I am master of all that is rectangles. 3, I think I can do these. I've got the notes and I'll have to dig into some of them and have some challenges, but I think I can do this. 1, I don't think rectangles are right. Excellent. By the way, do you guys know that recht comes from German, means right? That's why they're called that. Okay, second page. We are now going to look at rhombus, but not just one rhombus, but multiple rhombus. That's called rhombi. Let's do a little understanding of what we're talking about here first. What a rhombus is an equilateral quadrilateral. In other words, all 4 of these sides are the same. Now, what we often did when we proved parallelograms was we drew a diagonal, recognizing that that was reflexive. And what do we notice about these 2 triangles?
They're congruent by SSS.
Excellent. These 2 triangles are congruent, which allows us to say, for example, that opposite interior angles are congruent, kind of like in a parallelogram. And we could say that alternate interiors end up being congruent because you could spin it around, but it's unique because these triangles are isosceles. Not just is this angle the same as this, but this angle is the same as this, which is the same as this. Which means that this diagonal in a rhombus exactly cuts these angles in half. So if you knew that this whole angle was 80 degrees, for example, and this one was 100 degrees, you'd then know that each of these little ones is evenly split into 40. Some of you were tempted to do that with a parallelogram before, but it wasn't true. But it is true now for a rhombus. And that works both ways. Now, the other thing is, if we know that this angle is the same as this angle, and this angle, because it's half of that one, is the same as that one because it's also half, back when we did the triangle angle sum theorem, we had some corollaries. One of them was, if two angles in one triangle are congruent to two angles in another triangle, then the third angles must also be congruent. And if those two angles are congruent, and they also form a linear pair, what must be true about those two angles? They add up to 180.
They add up to 90.
They're each
Or
90.
like one, yeah.
They add up to 180, so they each have to be 90. They're right angles. So now in a rhombus, the diagonals bisect each other. So let's bring that into our notes here. So we're talking about the rhombi, the plural of rhombus. And a rhombus has all the same properties of a parallelogram. Opposite sides are parallel and congruent. Opposite angles are congruent. Consecutive sides or angles are supplementary, and diagonals bisect each other. In addition to that, we've now got the definition of a rhombus, which says 4 sides congruent. All 4 sides are the same. And like I just showed you with some quick proof, the diagonals bisect the interior angles. So that like these angles 4 and 5 will end up being the same, 1 and 2 will be the same, 7 and 6 will be the same. And diagonals are perpendicular. To make a right angle. So let's do number 2 here. I know that EF is 23. And I know that DF is 40. This is asking me to find GF. So how long is GF?
23.
Yeah. Because it's all sides are congruent, it's just going to be 23. What about HF?
20.
Good. Why 20?
Because it's half of DF.
Yep, because the diagonals bisect each other. All right. What about GH? There's one more piece to this picture that I just drew here. We know that the diagonals are now perpendicular, which means I can put a little right angle in there. And once I get a right angle, I can use Pythagorean theorem. There's a lot of that in this particular sheet, by the way. So 20 squared plus GH squared equals 23 squared. 400 plus GH squared equals 529. So GH squared equals 129. So GH equals square root of 129. Which is about 11.36. What about GE?
Would it be the square root of 258?
Right idea, but the 2 goes on the outside. It's going to be 2 times the square root of 129. If we were to bring that 2 on the inside, it would turn into the square root of 4. So you'd have square root of whatever that would be, 536 or something. 560. So it ends up being 22.72. Okay, and I don't want to do all the angle problems for you, but you'll have some angle problems. Let me just get you started on these. If this little angle here is 38, what other angle measure is also 38?
Angle 4.
Excellent, angle 4. You learned that from the parallelogram ideas, and that's still true here. But now there's new stuff. What other angle is 38? Good, Lindsay. Said angle 3, because these are now bisected, so they're both 38. One more is 38. Which one?
5,
Good. Why, Kirsty?
because it's split in half evenly.
Good. So if 4 is 38, so is 5. Or you could recognize that since these two sides are the same, this big triangle is isosceles. So if that's 38, so is that. Okay, these are just ways that you can think about the rhombus to help you remember the attributes. Any questions on attributes of a rhombus or properties of a rhombus? Okay, let's move on to our last shape of the day, the square. The square. You know, the square is such a regular shape, right? It's the regular quadrilateral. You'd think that it has some special elements to it, but actually what it's got is all the parallelogram stuff, all the rectangle stuff, and all the rhombus stuff, but nothing new. There's no secret sauce that magically appears when it's a square. It's just everything it stole from its neighbors. So for example, they tell us that AD is 11, and that's all. Well, that's easy for BC, isn't it? How big is BC?
11.
11, that's true because it's a parallelogram. What about AC? How am I going to find AC? If you're unsure, remember that you're dealing with a square. What are all the distinctive elements of a square? Well, all 4 sides are the same. So even though I haven't marked it yet, if these sides are 11, so is this, so is that. And it's got a rectangle, which means this is a right angle. Oh, do you see it?
Yeah, you can use Pythagorean theorem to find 11 squared, plus 11 squared equals AC squared.
Good. 11 squared plus 11 squared equals AC squared. So 121 plus 121 equals AC squared. So 242 equals AC squared. So AC is equal to square root of 242. And again, there's a value that, there's a way to simplify that and take it down to, what would it be, 16? I guess 4 wouldn't go into that. We'll learn about simplifying those later, so I'd be okay with you just leaving it like that, or a decimal approximation if you wish. What about BD?
Two 42 square rooted.
Yeah, because diagonals are congruent because a square is a type of rectangle. What about EC? Is that part of an angle, or is that part of a side, or is that part of a diagonal? It's part of a diagonal. Remember, diagonals bisect each other, so it's going to be half of that, which means it would be square root of 242 divided by 2. What about DAB?
90 degrees.
Yep. And AEB?
Degrees.
Yeah, because a square is a rhombus, right? It's a special type of rhombus, and rhombuses all have diagonals that are perpendicular. CBD. Well, I'm talking about angles. And I know that the whole interior angle is 90. Because this has rhombus attributes, it's going to split that in half. So that's 45. BAC is also going to be 45. Okay. Any questions on squares? Okay. Again, your homework will be to finish these up. So 1, 2, 3, 4, 5, 6, 7 problems here. And I want to introduce the coordinate geometry stuff now, and then I'll be able to put you in the breakout rooms for the remaining part of class to get started on this. You'll remember coordinate geometry is a way of proving something is true using algebra. And traditionally you use distance formula, midpoint formula, and slope formula. Last time we just used distance and slope formula. So I want to draw a little picture here. Of the 4 shapes we're dealing with today. And every one of these coordinate geometry problems will end up being one of these 4 shapes. But you don't know which one. It could be a parallelogram. It could be a rhombus. It could be a rectangle. Or it could be a square. Last time with parallelograms, we would find the slope of opposite sides and make sure that they're the same. And if we did it for those two and those two, we'd know it's a parallelogram. If we did that today, would that help distinguish any of these shapes? If I chose to find the slope of opposite sides, would that help me distinguish which shape it is? No, because they're all parallelograms. So we want to find distinctive features. How could I separate the top shapes from the bottom shapes? What's a difference? What unique attribute do these two have in common?
they form right angles.
And is there anything I could use the slope for to identify right angles? Like, let's say the slope of this came out to be 1/2. And I know this is a right angle. What would the slope over here be?
0.
Yeah, you're assuming that the picture is drawn in that direction. I'm thinking it's more like that. Because if this is 1/2, it's going up at a slant. But when two lines are perpendicular, how are their slopes related? If this is the slope of 1, it's perpendicular if the other slope is the negative reciprocal of it, where you flip it over and change the sign. So if this is 1/2, this slope would have to be -2/1. And if this was like -3/4, this slope would have to be +4/3. So one thing we could do is we could measure the slopes of two adjacent sides and see if they give us that relationship. So that helps us distinguish the top from the bottom. The top don't have perpendicular sides, the bottom do. How could I distinguish the right from the left?
On the right, the sides are congruent.
Yes. And because the sides are all congruent, if I were to take two adjacent sides and find their length, and they come out to be the same, then I know I've got either a rhombus or a square, right? Because these adjacent sides would be different. So let's put it all together. If I want to see what shape this is, step 1 is look at the slope of two adjacent sides. Slope of two adjacent sides. So for example, I'd say m equals, do we remember our slope formula? It's like that. So if I want to find the slope of, let's say, ST, I'd say y minus y or x minus x is -2/5. And now I need to find the slope of a different side. Which side should I pick?
UV.
If I picked UV, which is exactly what I taught you last time, what you'd be comparing is the opposite sides to each other. You'd find the slope of two opposite sides because they don't share any points. And because they're all parallelograms, that would definitely come out the same slope. So that wouldn't help us. We want to find the slope of two adjacent sides next to each other, sharing a
TU.
good. So let's choose like TU. We could have also chosen SV. But I'm going to take TU and find the slope of that. So 0 minus 10 over -3 minus 1 is -10 over -4, which is a +5/2. Does that do anything for us? What's true about these two slopes?
They're reciprocals.
They're negative reciprocals. Therefore, we can say that the sides are perpendicular. Now, for my purposes, I think what's really helpful is to actually have down here at the bottom, like the possible choices. It could be a parallelogram, it could be a rectangle, it could be a rhombus, or it could be a square. But the fact that we just discovered that these are perpendicular, which of these shapes can I cross out now?
The parallelogram and the rhombus.
Exactly. Those shapes don't have to have right angles. This does have a right angle, so the best name would be either rectangle or square. How can we distinguish between those two? So the second step is the lengths of two adjacent sides. Right? We want to see if it's a rectangle with one long side and one short side next to each other, or if it's a square where they're the same size. So we're not going to use the slope formula. Now we're going to use the distance formula. X2 minus x1 squared plus y2 minus y1 squared. That's our formula. And let's see what we're going to do. I'm going to find the distance first for ST. Use the same sides. So ST, so that's x minus x, so 1 minus negative 9 squared plus 10 minus 4, 14 squared equals 10 squared plus negative 4 squared, square root of 116. Okay, what else do I need to find?
The distance of TU.
Good. So I'm going to find the length of TU. So x first, negative 3 minus 1 plus 0 minus 10 squared, negative 4 squared plus negative 10 squared, 116, square root of 116. What does that tell me?
It's a square.
It tells me that it's equilateral, doesn't it? All four sides are the same. Therefore, it's either a rectangle or a square. It's not a rectangle. It has to be a square. So what shape is it? It's a square. Would you like to go into breakout rooms now, or would you like me to do one more? How about if I set up the breakout rooms, and then those of you that would wish to hang out and watch me do another one, I'll do another one. Those that want to go into breakout rooms can. It's going to take me a minute. I will set up the same breakout rooms as we had last time. If you're interested in changing, let me know. Okay. Sorry guys, because I don't use a different room for every class, it always takes me longer because I have to do this by hand. If I find the slope of two adjacent sides, first I'll find EF, and then I'll choose another one that's next to it, like FG. I remember my slope formula is the difference in the y's over the difference in the x's. So that's 1 over 9. And down here, I have a difference in the y's, -7 minus -3 over 0 minus 2. That's -4 over -2, which is 2. So what does that tell me? Not perpendicular. So if I write all my choices down here, parallelogram, rectangle, rhombus, and square, which ones can I cross out now? If the two adjacent sides are not perpendicular, it's not a square, it's not a rectangle. So now I'm going to find the lengths of two adjacent sides. Choose the same side, so I'll say EF. Can use my distance formula. So x minus x, 2 minus -7, y minus y, -3 minus -4. That's 9 squared plus 1 squared. 81 plus 1 is square root of 82. I'm just going to leave it like that. And then I need to find this length, FG. FG. So I'm going to take the difference in the x's, 0 minus 2, plus the difference in the y's, -7 minus -3 squared. -2 squared plus -7 plus 3 is -4 squared. So that's going to be a 4 plus 16 is 20, square root of 20. Interesting. So those are not congruent. So if they're not congruent, then it's not a square, it's not a rhombus. That's the one I have there. Leaving me with only one possibility. This must be a parallelogram. Okay, if you guys want to go into the breakout room, we got about 15 more minutes, I think. Give it a shot. We got 2 more coordinate geometry ones, and what did we say, about 5 of the shape-specific ones.